Look at the night sky and you encounter a strict physical constraint. No matter the power of our telescopes, stars remain zero-dimensional points of light. We cannot send probes to them. We cannot measure them with physical tape measures or thermometers. They are entirely out of physical reach. Yet across those immense distances, that single point transmits exactly 3 raw data streams we can directly detect: its apparent position on the sky, its apparent brightness, and the spectrum of its color. From those 3 narrow inputs, we extract the actual physical reality of the star. We must calculate its absolute distance, its total energy luminosity, its surface temperature, its physical radius, and its exact chemical composition. To bridge the gap between what we see and what actually exists, we rely on a mathematical pipeline. By applying geometric scaling laws and thermodynamics, we process those sparse observations into a detailed physical profile. Through this mathematical framework, we establish the mass, scale, and output of objects trillions of miles away, mapping the exact physical dimensions of the universe without ever leaving Earth. To determine any absolute physical scale in astrophysics, we have to find the absolute distance to the source. Distance anchors every subsequent calculation. We solve for distance using trigonometric parallax. As Earth orbits the Sun, our vantage point shifts by 2 astronomical units over a 6-month period. This orbital movement creates a baseline, allowing us to measure the apparent shift of a nearby star against the static background. Interstellar distances are massive, meaning this angle of shift is infinitesimally small. To process it, we use the small angle approximation. Derived from the Taylor expansion of tangent functions, this allows us to treat the relationship between a minute angle and a massive distance as a simple linear equation. This establishes our standard unit of astronomical measurement. If a star exhibits a parallax shift of exactly 1 arcsecond across a 1 astronomical unit baseline, it is exactly 1 parsec away. The geometry collapses into a clean equation. Distance is the inverse of the parallax angle, providing our first solved variable. By locking down this single measurement, trigonometric parallax anchors all of our theoretical astrophysics to a firm, measurable spatial reality. With the distance solved, move to the second observable parameter, apparent brightness. Astronomers measure this as energy flux, the precise amount of energy passing through a specific area over time. A star radiates an expanding sphere of light. As the energy spreads thinner, a fixed detector captures exponentially fewer photons at greater distances. This dictates the inverse square law. Measured flux equals absolute luminosity divided by the expanding sphere surface area, 4 pi times distance squared. By combining the measured flux with the absolute distance solved in the previous step, we have the necessary variables to isolate the star's actual power output. We algebraically reverse the flux equation. By multiplying our locally measured flux by the total surface area of that vast distant sphere, we isolate the star's absolute luminosity.
This calculation strips away the optical illusion of distance, separating how bright a star appears in our telescopes from the sheer volume of physical energy it generates in a vacuum. Next, we extract data from the star's color spectrum, treating the star initially as an idealized thermodynamic object known as a blackbody. Planck's law dictates a blackbody's spectral curve depends entirely on gas temperature. Raising temperature increases intensity and shifts the peak to shorter wavelengths. Overlaying the visible spectrum shows a 5800 Kelvin star, like our Sun, peaks perfectly near 500 nanometers, producing its distinct hue. This inverse mathematical relationship between a star's peak emission wavelength and its surface temperature is defined as Wien's displacement law. By identifying the exact wavelength where a star's flux peaks, we invert the calculation to extract its exact surface temperature. The third variable locks into place. A star's temperature is encoded directly into its color, giving us a precise thermal reading from light years away. We now face the radius problem. Due to extreme distance and atmospheric blurring, it is physically impossible to optically resolve a star's surface area. To solve for size, we introduce the Stefan-Boltzmann law, the thermodynamic bridge connecting absolute luminosity, surface temperature, and physical radius. The Stefan-Boltzmann law dictates a star's absolute luminosity is determined by its surface area multiplied by the 4th power of its temperature. With luminosity and temperature already solved, we rearrange the formula to isolate the final unknown variable, extracting the star's exact physical radius.
By synthesizing these specific thermodynamic laws, we measure the physical size of an object smaller than a single pixel in our lenses. Our model requires one final correction. Real stars are not perfect blackbodies. Their thermal spectra contain specific missing data points. This image shows a solar spectrum. It is marked by a complex pattern of dark absorption lines cutting vertically across the bright, continuous colors. These lines are caused by quantum mechanics. As photons from the hot core travel outward through the star's cooler upper atmosphere, they collide with atoms. Because electrons exist in discrete energy levels, they absorb only the specific photons, providing the exact energy required to jump to a higher orbit. Each element has a unique electron structure and absorbs a distinct set of wavelengths. These missing lines act as chemical barcodes, revealing the exact atomic composition of the stellar atmosphere. Furthermore, the degree of atomic ionization depends directly on the surface temperature. This chart displays the OBA-FGKM stellar classification sequence. The dark absorption line patterns shift entirely depending on the star's heat class, providing an independent diagnostic of its thermal state. We now possess a complete observational pipeline. We observe a single point of light, measure its position to calculate distance, track its brightness to derive luminosity, and read its color to find temperature, scale, and atomic composition. The night sky is a dense, high-fidelity transmission of physical data. Every star broadcasts its exact mass, scale, and output, fully decipherable to anyone applying the first principles of astrophysics.